Okay, so let's go ahead and continue talking about these waves in motion. Last section we went ahead and we looked at talking about wave speed calculated by taking the wavelength times the frequency. Well, let's go ahead and look at what happens when waves go through some different interactions. We've talked about some of these properties. We talked about amplitude. We talked about wavelength, but again, a lot of that was going to be with waves standing still. And again, we know that those waves are going to be in motion. So what we want to do is we want to see how they act around different surfaces, whether it be striking the surface directly, whether it be striking the surface at an edge, and we also need to see what happens when these waves also encounter one another. As waves are traveling, they're constantly encountering lots of different boundaries, lots of different surfaces through which they cannot pass through. For example, light, it can pass through a window, but we're going to talk about surfaces right now that they cannot get through. And if they cannot get through that surface that they strike and they bounce off of that surface, that's going to be reflection. Maybe you've talked very loudly, maybe you've been in an auditorium where you hear that echo. That's just going to be your sound wave that's going to be bouncing off of a wall, coming back to you, and that's what you end up hearing. So when we look at this law of reflection, I'm going to put a couple of words up here. So this angle at which this wave comes in and hits the surface, that's the angle of incidence. The angle at which it leaves that surface, that's going to be the angle of reflection. The angle of incidence is going to be the one right in here measured with respect to that perpendicular. The angle of reflection is just going to be the angle at which it bounces off. And I'm hoping that if you go ahead and examine those two angles, you should notice that they are going to be similar or they are going to end up being the same. Now this is going to occur when the surface that it is hitting is going to be perfectly smooth. And if it bounces off at the same angle at which it approached, that's going to be that law of reflection. The angle of reflection is going to be equal to the angle of incidence if the surface is smooth. But what if that surface isn't smooth? Well, then you get something like this occurring. You've got a wave of light coming in, hits an uneven surface, maybe hits a cracked window, something like that. And the angle of reflection, well, we really don't know what angle it's going to be bouncing off of. So we saw what happened when it hits a surface directly, bounces off, that's going to be reflection. But what happens when it strikes the edge of a barrier? When it strikes the edge of a barrier and wraps around that barrier, that's when you're going to notice diffraction occurring. Now, diffraction, it's that wave that bends around a barrier, bends around a surface. Let's go ahead and talk about this. Let's say you let the dog out the front door and you realize, okay, it's time for the dog to come back in. Maybe it's time for the dog to eat. You go out the front door and the dog's nowhere to be found. You yell for the dog, and all of a sudden the dog comes running around from the side of the house. Well, as your sound waves were being directed straight ahead, out that front door, they were spreading themselves out. As they were spreading themselves out, they were going around the side of the house, and maybe the dog was in the backyard and heard you. Maybe the dog was around the corner, but the dog comes running because it heard your sound waves as it spread around the side of the house. If we go ahead and we look at this simulation here, so we have these waves that are going to be in motion as we watch it. The only thing I wish it showed the reflection occurring as it hits the wall. But as you follow those waves, you're going to notice that most of the darker waves on the right side are going straight ahead. How it is fanning out. A little bit lighter on the top and bottom, but that's just still, the wave is a little bit weaker. Completely around that spread itself out. Now let's go ahead and talk about waves as they go from one medium into another. So maybe we're talking about air and water. Well, here's kind of what I mean. If you're driving on the highway, and we're going to say we got a little bit of rain, and the shoulder is right now a muddy shoulder. If the right side of your car drifts onto that shoulder where it's mud, that mud's going to slow your car down on the right side, slow those tires down. Well, the tires that are on the left side, they're still up on the pavement, maybe doing 60, 65 miles an hour. And what you'll notice is your car will get pulled towards the ditch, okay, or pulled towards that muddy shoulder, because you have one side of the car that is traveling slower than another side of the car. Maybe here's another way of thinking about it. It won't be the bending, but it's a good way to think about it. Waves travel at different speeds in different materials. So let's say it's a hot summer day, you're at the pool, and as you are walking or walking quickly to get into the pool, you're walking on the pool deck and you're moving pretty fast. But think about now jumping into the water, and think about now trying to walk just as quickly. You can't walk as quickly because the water is thicker. The water is more dense and it's going to slow you down. You can't travel at the same speed in the water because your speed is different because of the density of the different mediums. So waves are able to change their direction from one medium into another. Okay, and there's going to be an apparent bending of that wave, and that apparent bending is going to be refraction. And refraction is just going to be a wave's change in direction as it moves from one medium into another. So let's say we're going out spearfishing. I've actually used this as an example. People going out and using a bow and arrow to hunt fish, okay, or shoot fish. And the thing is, the fish isn't where you think it is. Because, see, right now this person here is looking in the air. Okay, so as you follow that light wave, they are looking in the air. But where's the fish at? The fish is really in the water. Okay, the fish is going to be down a little bit lower, because if you throw that spear or you shoot that arrow where you think that fish looks to be, well, you're going to miss that fish. That spear is going to go right over the top of the fish. So really, in reality, you need to aim a little bit lower. Aim below where that fish is going to be, because again, you're looking in the air when the fish is actually in the water. So that wave of light that we are looking at appears to be bent, or it is going to be bent, because the fish really isn't where it is. You know, I challenge you, while you're at home, go ahead and get a clear glass and put a pencil part way into it. So part of the pencil sticking out, or the spoon is sticking out, and look at the spoon from the side. You're going to find out that that spoon or pencil appears to be bent or appears to be broken. And the reason being is part of the pencil or spoon is in the water where it's thicker, but part of you looking at it is going to be in the air. So when we look at it and you follow that wave of light in, so up top you're finding out that it is in the air, but when it goes through the glass is thicker, more dense. You're going to find out that that wave is going to bend in that glass, slow down, because it is thicker and cannot travel the same way. But when it comes out, that top line in light and that bottom line, those should be parallel to one another. But again, it's going to be that bent light wave as it travels from one medium into another. Let's go ahead and let's talk about these waves as they encounter one another. So when waves come into contact with one another, what it's going to do is it's going to mix their amplitudes. It's going to mix those crests, or it's going to mix a crest and a trough. Maybe you've been traveling, and as you're traveling, you're listening to your favorite radio station, and we're going to say you get a little bit further from where the radio station is, Lincoln, Omaha, wherever. And all of a sudden, as you're listening to your favorite song, it starts to crackle a little bit, starts to break up. That's because there's going to be an interference from a frequency from maybe another radio station that is near the radio station's frequency that you're listening to, and it causes that sound to mix. Sometimes it's coming in clear as can be, and sometimes it's really crackling and breaking up your favorite song. There's going to be two types of interference. Those two types of interference, the first one is going to be constructive interference. Constructive interference, when you construct something, you build it bigger, you make it bigger. It says here, when two or more waves combine to form a single wave that appears to have a greater amplitude. I'm going to tell you, constructive interference is a crest meeting a crest, two crests adding together, or two troughs adding together. If I get one wave that's a 3 and one wave that's a 2, both of them being crests or both being troughs, just like constructive interference says, they're going to add together. They're going to make a bigger wave. So we're going to take the 3 plus the 2, and all of a sudden it's going to build a wave for a split second that appears to be 5 meters tall. Or it's going to take a trough of 3 and a trough of 2, and it's going to build a bigger trough that's going to end up being 5. So you simply take the waves and addition, add them together to find the resulting wave or single wave for constructive interference. If we can build things up, we can also tear things down. Destructive interference. Two or more waves combine to form a smaller amplitude. So this is going to be a crest meeting a trough. And if we want to get something smaller, we end up subtracting. So let's say we have a 3-meter crest and a 2-meter trough. The resultant, 3 minus 2, because the crest was bigger, is going to be a 1-meter crest. Now, it doesn't always have to be a crest. We could take a 5 trough and a 2 crest. Okay, 5 going down, 2 going up. So when they meet, you're going to find out that the trough was bigger. So 5 minus 2 is going to give you a 3-meter trough. Again, if we go ahead and we look at a simulation. Okay, looking at this simulation in full motion, you're going to see it appears to be building a bigger wave and then all of a sudden building that smaller wave. So I'm going to go ahead and let it go back through one more time. And then what I'm going to do is I'm going to go ahead and slow it down. Okay, so getting them going towards one another. Okay, so as they go towards one another, okay, notice right now as they are coming together, I have a crest on the left side meeting a trough on the right side. Again, it is a red and blue, the initial waves. It says up top wave 1 and wave 2. One's red, one's blue, but watch that white line. Okay, notice how that white line is going down to nothing. Basically right now we have complete destructive interference. The height of that red wave is canceling out the height, or the, I guess, bottomness, okay, or the trough of that blue wave, resulting in something right at rest position. Now as they continue on, notice I have a blue trough coming in and a red trough coming in, and all of a sudden you're going to notice that it appears that that wave is getting bigger. Notice again on the right side I've got a red crest meeting a blue crest, and notice that wave all of a sudden as they get almost over the top of one another. Okay, notice this wave should almost be twice as big as the red and the blue crest, or notice that white trough wave should be almost twice as big as that red and blue, because they are completely adding together to get that bigger wave. So I'm going to go ahead and just put it in motion, get rid of the slow motion, and let you watch it again before we end up finishing. So crest meeting a trough, cancels out, and then all of a sudden they come back together to form constructive interference about right in here.